Have you ever gazed up at the night sky and wondered about the enigmatic secrets held within the twinkling stars? Today, we embark on a voyage beyond the familiar, delving into the realms of theoretical stars, entities that defy our conventional understanding of the universe. Join us as we uncover the extraordinary phenomena that shape our universe. From the fiery birthplaces of stars to the mysterious realms of dark energy, we'll unravel the mysteries that have captivated astronomers and astrophysicists alike. But this isn't just a journey of observation, it's an exploration of the theories and speculative wonders that push the boundaries of our comprehension. As we dive deep into the realm of hypothetical stars, we invite you to join the conversation and share your thoughts and questions along the way. So, buckle up and don't forget to subscribe to our channel for more captivating space-related content that will ignite your imagination and expand your understanding of the universe. Let's embark on this adventure together. First, we need to lay some groundwork and understand how stars work in general, starting with the most important star of all, the Sun. Since the Sun is made of gas and not solid matter, you couldn't stand on its surface like you would on the Earth. The Sun's gravity would just pull you down toward the center. So why doesn't the gas at the surface get pulled inwards too? It turns out that there is a pressure pushing outward from the Sun's core that counterbalances this pull of gravity. The main source of this pressure is the radiation created by fusion reactions in the core, the same radiation responsible for carrying light and heat from the Sun to the Earth. Radiation, whether you see it as tiny particles or waves, travels from the Sun's core to its outer layers. It pushes outward in all directions like a gentle breeze. This force isn't strong enough to push you away, but it keeps the Sun's gas from collapsing. All stars, like the Sun, balance between gravity pulling in and pressure pushing out. But what makes stars unique is where this pressure originates. For our Sun, the pressure comes from fusing hydrogen into helium. When the Sun runs out of hydrogen in about 5 billion years, it will become a red giant star, whose pressure comes from fusing helium into even heavier nuclei. Eventually, the Sun will also run out of helium and any other light elements that could be used as fuel for nuclear fusion. At that point, it will collapse into a small star known as a white dwarf. Since no more fusion is occurring anymore, white dwarfs are sometimes called stellar remnants instead of stars. But if there's no more fusion, where does the pressure to support these stellar remnants come from? It turns out that gravity pulls the gas of a white dwarf inward until it's so dense that a new type of pressure emerges, known as electron degeneracy pressure. This is a purely quantum mechanical effect, and it's the same effect that's responsible for you not being able to pass your hand through solid objects. Electrons simply cannot get too close to each other without an extraordinary amount of energy. However, some leftover star bits are so hefty that even the push from electrons isn't enough to stop gravity's tug. This is the Chandrasekhar limit, a strict boundary that says no white dwarf can be heavier than 1.4 times the Sun's mass. If a star's core surpasses this limit after burning up all its fuel, it caves in on itself. This collapse creates a super-dense core where an even stronger force, called neutron pressure, comes into play. This force, like a cosmic bouncer, keeps particles from crowding too close together. When a star shrinks down this much, it becomes a neutron star, the tiniest, densest stars known to us. Now you might wonder, is there a weight limit for these stars to stay afloat on neutron pressure? Indeed there is. It's around 2.2 times the Sun's mass. If a neutron star gets any heavier, gravity wins the tug-of-war, and the star keeps squeezing itself tighter. Eventually, there's no stopping it. Neutron pressure is like the ultimate bodyguard for matter, but even it has its limits. Some of the universe's heaviest stars might meet this fate. From the perspective of an outside observer, these stars would get so dense that all we'd be able to see is a black hole. But then scientists started to wonder what would happen to a star that wasn't made of ordinary matter. If exotic forms of matter could hypothetically produce even larger pressures than neutron degeneracy pressure, then what new kinds of stars could exist? You might think that we could just continue the pattern that we were starting to see earlier. Stars could get even smaller and even denser than neutron stars, as long as they were supported by some even greater pressure. You might think that the only limit on how small these stars could get would be the point of no return, where they would turn into black holes. That point of no return is when a star becomes smaller than its own Schwarzschild radius. This is almost true, but not quite. Back in 1959, physicist Hans Adolf Buchdahl uncovered a fascinating fact. He found that any star made of regular stuff with positive energy and pressure can't shrink smaller than 9/8 of its Schwarzschild radius. Sounds a bit technical, right? But this discovery has big implications. It means stars are inherently bigger than black holes, making them stand out in the cosmic crowd. That got physicists wondering, what about stars that don't play by the rules? For example, what if a star was made of matter that allows for pressure to be negative in some regions and positive in others? Then Buchdahl's limit wouldn't apply, and that star could be less than 9/8 times its Schwarzschild radius. In fact, it could be arbitrarily close to the size of a black hole with the same mass. As a side note, theoretical stars like these that could mimic the appearance of black holes came to be quite a nuisance for astrophysicists, since now every time they discovered something they thought was a black hole, they couldn't just say they discovered a black hole. They had to qualify that it's either a black hole or an extremely compact object mimicking a black hole, even though in their hearts most of them are quite convinced that it's a black hole. But to the main point, what would these exotic stars with negative pressures even look like? This theory has layers waiting to be peeled back, sparking curiosity and deeper thinking. What's your take on this journey so far? Share your thoughts in the comments. We've only scratched the surface of the mysteries lurking in the depths of space. Want to dive deeper into the wonders of space science? Subscribe to Space Episodes for upcoming educational videos related to space science, and press the bell icon. Thank you for watching this video until the end.